Imagine a place in the cosmos where the rules we know seem to break down. A place where gravity is so strong, so incredibly powerful that nothing can escape its grasp. Not a planet, not a star, not even the fastest thing in the universe, light itself. This is a black hole. It is not an empty hole or a void in space. Instead, it is a tremendous amount of matter squeezed into an impossibly small area. Think of the entire Earth crushed down to the size of a tiny sugar cube. The result is an object with a gravitational pull so immense that it warps the very fabric of space-time around it, creating a deep well from which there is no return. The story of a black hole often begins with the dramatic death of a massive star. Stars are giant nuclear furnaces, constantly balancing the inward crush of gravity with the outward push of nuclear fusion in their cores. For millions, sometimes billions of years, this cosmic battle rages on. But all stars eventually run out of fuel. For the most massive stars, those many times heavier than our own sun, the end is catastrophic. When their fuel is spent, the outward pressure vanishes. Gravity, the patient and relentless force, wins the final battle. The star's core collapses in on itself with unimaginable violence, triggering a spectacular explosion we call a supernova. What remains after this stellar explosion is a testament to gravity's ultimate power. The core of the dead star continues to collapse, shrinking smaller and smaller, becoming denser and denser. All that mass, once spread out across a giant star, is now concentrated into a single point of infinite density called a singularity. This singularity is the heart of the black hole. It is here that our current understanding of physics falters, where the laws of nature as we know them cease to make sense. The birth of a black hole is one of the most violent and transformative events in the entire universe, a moment where a brilliant star becomes a ghost in the dark. So why are these cosmic objects so dark? It comes down to that inescapable gravity. Light travels in straight lines through space, but when it passes near a massive object like a star or a planet, its path is bent by gravity. A black hole takes this to the extreme. The gravitational pull is so intense that it creates a boundary around the singularity known as the event horizon. Any light that crosses this boundary is trapped forever. It can no longer travel outward, it can only fall inward. Since no light can escape to reach our telescopes, the black hole itself appears perfectly black against the backdrop of the star-filled cosmos. It's a shadow cast in space-time. The event horizon is the most famous feature of a black hole. You can think of it as the ultimate cosmic waterfall. Far away, the river of space-time flows gently, but as you get closer to the black hole, the current gets stronger and stronger. The event horizon is the edge of that waterfall, the point of no return. Once you cross it, the current of space-time is flowing inward faster than the speed of light. Since nothing can travel faster than light, escape becomes impossible. It doesn't matter how powerful your rocket ship is. You are now part of the black hole. It's a one-way trip into the unknown, a boundary separating our universe from whatever lies inside. This powerful gravity doesn't just pull on light, it pulls on everything with mass. Any star, planet, or cloud of gas that wanders too close gets caught in its gravitational web. We can't see the black hole directly, but we can see its effects on the things around it. We can observe stars orbiting what appears to be empty space, moving at incredible speeds. This frantic dance is a giveaway, a gravitational signature that tells us a massive invisible object must be hiding there. Sometimes, as matter is pulled in, it forms a swirling disk around the event horizon, known as an accretion disk, which heats up and glows brightly, giving us another clue to the black hole's presence. What makes black holes so special in the grand cosmic theater is their sheer simplicity. While a planet or a star is a complex object with chemicals, weather, and intricate structures, a black hole is defined by just three things: its mass, its spin, and its electrical charge. That's it. All the complex information about the star that formed it is lost forever, a concept that has puzzled physicists for decades. They are the ultimate expression of gravity's power to smooth out all details, to reduce the complexity of the universe to its most basic properties. They are nature's most perfect and most mysterious objects. The pull of a black hole is a demonstration of Einstein's theory of general relativity in its most extreme form. Einstein taught us that gravity is not a force, but a curvature in the fabric of space-time caused by mass and energy. A bowling ball on a trampoline creates a dip, and a marble rolling nearby will curve toward it. A black hole creates a bottomless pit in that trampoline. The closer you get, the steeper the slope, until you cross the event horizon where the slope is vertical. This warping of space-time is so profound that it even affects time itself. For an observer watching from a safe distance, a clock falling into a black hole would appear to tick slower and slower, eventually seeming to freeze at the event horizon. Black holes come in a surprising range of sizes, from stellar mass black holes to the colossal supermassive black holes. The smallest ones, known as stellar mass black holes, are typically between 3 and 20 times the mass of our Sun. They are the common kind, scattered throughout galaxies like our own Milky Way, the quiet remnants of long-dead giant stars. These are the black holes born from the supernova explosions we discussed earlier. While they are small by cosmic standards, their gravitational pull is still immense, capable of tearing apart a companion star if it strays too close for comfort. They are the silent predators of the galaxy. Then there are the titans of the cosmos, supermassive black holes. These behemoths are millions, or even billions of times more massive than our Sun. We believe that nearly every large galaxy, including our own Milky Way, has a supermassive black hole at its very center, acting as a gravitational anchor around which everything else orbits. At the heart of our galaxy lies Sagittarius A*, a supermassive black hole with a mass of about 4 million suns. How these giants formed is still a major cosmic mystery. They might have started small and grown over billions of years, or they could have formed from the direct collapse of massive clouds of gas in the early universe. Can a black hole grow? Absolutely. In fact, that is its primary activity. A black hole is an insatiable eater. Anything that crosses its event horizon, gas, dust, stars, or even other black holes, is added to its mass. As it consumes more matter, its mass increases, and the size of its event horizon expands. This is how supermassive black holes are thought to have reached their incredible sizes, by feasting on the dense concentration of stars and gas at the galactic center for eons. It's a slow but steady process of cosmic consumption, where the black hole's gravitational influence grows with every meal it pulls in from its surroundings. So, do these cosmic monsters last forever? For all practical purposes, yes. A black hole cannot be destroyed by any conventional means. Crashing something into it will only make it more massive. They are the most stable and long-lasting objects in the universe. However, the brilliant physicist Stephen Hawking proposed a way for them to eventually disappear. He theorized that due to quantum effects near the event horizon, black holes very slowly lose mass through a process now called Hawking radiation. But this process is incredibly slow. For a typical stellar mass black hole, it would take longer than the current age of the universe to evaporate completely, ensuring their reign lasts for an almost unimaginable time. While a black hole itself is dark, its surrounding environment can be one of the brightest places in the universe. As matter is drawn toward the event horizon, it doesn't fall straight in. Instead, it gets whipped around at incredible speeds, forming that glowing superheated structure called an accretion disk. The friction within this disk of spiraling gas and dust generates immense heat, causing it to shine brilliantly across the electromagnetic spectrum, from radio waves to X-rays. In fact, some of the most luminous objects we can see, known as quasars, are powered by supermassive black holes actively feeding on enormous amounts of matter at the centers of distant galaxies. This process of feeding is not always neat and tidy. Sometimes, as matter swirls in the accretion disk, powerful magnetic fields get twisted up and act like a cosmic slingshot. They can launch enormous jets of particles and energy away from the black hole at nearly the speed of light. These jets can extend for hundreds of thousands of light years, far beyond the host galaxy itself. So paradoxically, these objects known for pulling everything in are also responsible for some of the most powerful explosions and energy emissions in the cosmos. The black hole doesn't emit this energy, but its immense gravity is the engine that powers this spectacular cosmic show. Then there is the theoretical glow predicted by Stephen Hawking. Hawking radiation is a mind-bending concept that arises from the strange rules of quantum mechanics. The vacuum of space is not truly empty. It's filled with pairs of virtual particles that pop into existence for a moment before annihilating each other. Near an event horizon, it's possible for one particle of a pair to fall into the black hole while the other escapes. To an outside observer, it looks as if the black hole is emitting a particle. This slow leak of energy causes the black hole to lose mass, but the process is so faint and slow that we have not yet been able to detect it. Black holes capture our imagination because they represent the edge of our knowledge. They are laboratories for testing the limits of physics, where gravity, space-time, and quantum mechanics collide. They challenge our deepest intuitions about the universe. They are born from the death of stars and can shape the evolution of entire galaxies. They are both simple in their structure and infinitely complex in their implications. From their inescapable darkness to the brilliant light of their accretion disks and powerful jets, black holes remind us that the universe is filled with wonders that are more extreme and more fantastic than we could ever dream. They are a fundamental and fascinating part of our cosmic story.